I've been wanting to give this talk for a while to try to convince the community, or at least push back on the community, that MAD is not the solution to all questions in accretion physics. And so I'm basically going to be going through and sort of summarizing results that I published in a paper last year. It's a pretty simple argument, but I will go through a lot of the background for those of you who don't study X-ray binaries as much as I do. So the systems that I'm talking about in particular, I'm talking about low mass X-ray binaries. So these are binary systems where one of the objects is a compact object, either a neutron star or a black hole. It's in orbit with a companion star that's usually an ordinary main sequence star, maybe early post-main sequence star. The star is overflowing its Roche lobe. Material falls off of that star towards the compact object. And because of conservation of angular momentum, it circularizes, forms this accretion disk, and slowly works its way onto the compact object. I'm going to be focusing today specifically on black hole X-ray binaries. And just to remind you, for reasons we still don't fully understand, accretion disks across nature seem to often be associated with jets, these narrow, fast outflows, and then often also with winds, which are maybe wider, slower outflows. And so they're called X-ray binaries, these low mass X-ray binaries. If you just look, for instance, estimate what the temperature in the accretion disk itself is going to be. So here's sort of analytic estimate of the temperature, or plots of the temperature as a function of radius. And the point is they get to temperatures of 1 million, 10 million Kelvin, or even hotter. So if you just think in terms of black body emission, that would be in the X-ray part of the spectrum. So these emit most of their radiation in X-rays. This is sort of a cartoon, again, for those of you who don't study these X-ray binaries a lot, or black hole accretion, to kind of give you an idea. It's really just to illustrate. So here we have an actual spectrum from one of these systems. This is a particular one that I'll mention multiple times, called GX339-4. The point is the spectrum is actually made up of multiple components, or the argument is that it's made up of multiple components. So there is the accretion disk, and the accretion disk emits roughly as a multi-temperature black body. But that part of the spectrum, it peaks at about 1 keV, so in what we call the soft X-rays. This particular source, in this particular observation, most of the X-rays are actually coming out in the harder parts, so tens of keV. And we think that, well, observers attribute those hard X-rays primarily to something they call the corona, in analogy with the sun's corona. But I would argue we don't really know a lot about where that corona is, or what that corona is in the case of X-ray binaries. And then there can also be other components that I'll mention later as well. For instance, a reflection component, where, for instance, maybe the corona is shining back down on the accretion disk, and then that material is being reflected and contributing to your observed spectrum as well. All right, so just to give you some orientation about what the spectrum and the components of the spectrum are. And so I'm going to be talking, these X-ray binaries are actually, most of the time, they spend most of their life in quiescence. So you don't see them, you don't even know they're necessarily there. They become discovered when they go into outbursts. And these outbursts can last from days to weeks to months. A few sources have been in outbursts since they were discovered decades ago, but that's pretty rare. So here's a particular example of an outburst of that same system, GX339. And this outburst lasted for approximately 300 days, so roughly a year. And all of the black hole X-ray binaries, when they go into outburst, seem to follow a similar pattern. And that pattern shows up well, for instance, if you plot it in what's called a hardness intensity diagram, which this is an example of. So on the horizontal axis, you plot spectral hardness. So is most of the emission coming in hard X-rays, or is most of the emission coming in soft X-rays? And on the vertical axis, you plot the brightness or luminosity or X-ray count or something. So this is something like an HR diagram for stars, except for X-ray binaries, okay? So something like a color and a brightness. And the points over here, so this is just the light curve of the outburst. So it's not visible, and then suddenly it brightens and becomes visible, and eventually dims and becomes invisible again. But they're color-coded so you can keep track of where you are in the outburst. So blue color is early in the outburst, and teal, green, moving into orange and red later in the outburst. And so now you can follow what happens in the hardness intensity diagram during the outburst. So we start on the hard part of the diagram, and it rapidly rises in brightness, but staying hard. So we start down here, and we rapidly reach this point. And then at some luminosity, and this luminosity varies a little bit from outburst to outburst and source to source, but at some luminosity, the brightness stops going up, and the accretion system decides it wants to switch into a soft state. So it moves over to the left side of the diagram, and then it might bounce around for a little while over here. Some of them even occasionally go back to that side and then come back to this side. Later in the outburst, the luminosity starts to drop, and it moves down on the soft side. And then at a very particular luminosity, it seems all of the sources then switch back over to the hard state and eventually fade out, all right? And so in my talk, or my title, I said, the luminous hard state can't be mad. And so I just want to focus in, what I mean by the luminous hard state is the hard part of this diagram, but up here at the high brightness, what are sometimes called the hard intermediate state up here, but even the upper part of just the ordinary hard state. So that's where I'm focusing on in this talk. All right, and so then I said the luminous hard state can't be mad. So just in case anybody here doesn't know what I mean when I say MAD, so MAD is an acronym for magnetically arrested disks. The basic idea is so black holes themselves don't have intrinsic magnetic fields, but an accretion flow could feed magnetic fields down to a black hole. And there's a limit at which if you feed enough magnetic field onto the black hole, you can essentially saturate the black hole and build up enough magnetic field around the black hole that the magnetic pressure is then able to prevent additional accretion, to prevent the gas from being able to fall into the black hole. And so that's what we mean by magnetically arrested. In this case, this is a two-dimensional simulation. And so after some amount of time, enough material builds up that the ram pressure eventually just forces its way through, and the material reaches the black hole. But then the magnetic field is going to restore itself, and it'll block the accretion again, and it'll just keep cycling through this. In a real three-dimensional system, you can also have interchange. Sorry. So, is there a question? Is that?
No, I think it's good.
Okay. In 3 dimensions, you can have interchange instability because you basically have low density, highly magnetized material trying to hold back high density, low magnetization material. So they're subject to interchange instabilities. And so the material is going to, the dense material is going to find a way to sort of pinch through. And then you're also going to have these sort of low density fingers of highly magnetized material. So it takes on a very non-axisymmetric, very chaotic sort of structure where mass accretion rate can fluctuate up and down quite a bit. And so it's its own sort of a thing. And so you get these periods where, some of the parts of the disk are blocked from reaching the black hole, other parts reach it. So this is a movie. I just borrowed this from online. The left-hand side is sort of a, you might consider sort of a typical accretion disk where you just have steady accretion flow onto the black hole. And the right-hand side is a MAD simulation. And so the biggest thing, so again, we're just kind of slicing through the disk here. The left-hand side is just sort of steady accretion through the whole simulation. What you see in the MAD flow is you get these interruptions, these big jumps where the disk will sort of detach from the black hole and then reattach. And so a very chaotic structure. There also tend to be much more inflated vertically. So it's a different kind of accretion. It's sort of its own thing. All right. Okay, so my hope at the end is to convince you that the luminous hard state can't always be MAD. The way I'm going to get there is by arguing about a model for what are called type C QPOs. So QPOs are quasi-periodic oscillations. So these are brightness oscillations that are seen in the X-ray light curves of many or most of these X-ray binaries. So this is a particular case of a QPO where you can actually see the oscillations in the period folded light curve of this particular source. Most of the time, the QPOs are discovered by basically looking in Fourier space. So you take the light curve, you Fourier transform it, you look at the power as a function of frequency, and the QPOs show up as a spike in power. And this also tells you why they're called quasi-periodic oscillations, because you can see that this peak has some width to it. So it's not a single frequency, it has some finite width to it. So it's not periodic, but quasi-periodic. All right. So in the black hole systems in particular, these black hole X-ray binaries, these QPOs are sort of divided into two broad categories. High frequency, which is usually 100 hertz or above, but there's one source where it's at 64, and so they say 60 or above. The low frequency tend to not get past about 30 hertz, so there is some break in the frequencies between the two. This is one source where we actually see both the high frequency and the low frequency at the same time in the same observation. And there's actually two high frequency QPOs, one at 300 hertz, one at about 450 hertz, and then simultaneously a low frequency QPO at just above 10 hertz. So I'm going to be focusing on the low frequency QPOs. I'm not going to go much into this, but the low frequency QPOs are further divided. This is mostly for anybody who's an expert in this. They're further divided into type A, B, and C. I'm going to only be focusing on what's called the type C QPO. Okay, so if you know anything about A and B, I'm not talking about those today. What I'm going to argue is that the type C QPO is well explained by something called lens-Turing precession. So now I'll try to just briefly explain what lens-Turing precession is. So lens-Turing precession is it's a relativistic effect around a rotating compact object. As the name implies, it's a precession. It's a precession that's caused by the rotation or the frame dragging of the black hole itself. So one way to try to illustrate it or motivate it is to show you sort of where it comes in. So there are people in the room at least who do fluid dynamics. So if you're familiar with Euler's equation, this is basically Newton's form of the Euler equation if you ignore this last term here. So then this last term is the lowest order post-Newtonian term. So it's a way to see where this lens-Turing precession comes from. So this term is just the fluid velocity crossed with this vector h, and h just depends on the angular momentum of the black hole, okay? And there's two pieces. There's one that points in the direction of the angular momentum of the black hole, and one that points in the radial direction. And so if you assume that the motion is mostly azimuthal, so this is an accretion disk, and so you cross that with this H vector, you basically get two terms, okay? So you get one term that acts in the sort of radial direction, and this is sort of a supplement to the normal, if you think in terms of like a centrifugal force. And it can actually act to increase the centrifugal force or subtract from the centrifugal force, depending on whether you're talking about prograde orbits or retrograde orbits. And the other term, which is the one that I'm interested in, first off, this term depends on, so theta here is the tilt angle of the orbit. So if the orbit is not tilted, then this term goes away. There's no precession, okay? But if the orbit is tilted, this is a force that acts in the vertical direction. So you have something with angular momentum at a tilt, and you have a vertical force, and the result is going to be precession, and that's what we call Lenz-Turing precession. So Lenz-Turing precession, one of the things to notice, it's strongly radially dependent. So it's strongest very close to the compact object and gets weaker further out. And so the result of that is it's going to tend to want to try to twist up the disk. And so, for instance, if you imagine that an accretion disk is just a series of non-interacting rings of particles just kind of going in circular orbits, then the effect would be you would rapidly twist up the inner part of the disk, and then slower and slower and slower twisting as you go further and further out in the disk. But what we know and what we find in practice is, of course, disks are not non-interacting rings of particles. They interact with each other. And so you get a different result. And so this was some of the work that Jordi was mentioning that I did a while ago, doing simulations of relatively compact, relatively thick disks. So, you know, tens of gravitational radii extent of the disk. This is a GR-MHD simulation. So there's magnetic field that's going to drive accretion. It's onto a rotating black hole where the rotation of the spin axis of the black hole is straight up and down in this. The movie on the left, we're looking at gas density, kind of a cutaway where you see the back half of the disk. And then in the upper right over here, we're going to plot twist. So the twisting of the material as a function of radius, and then here tilt as a function of radius. So this simulation started with a 15-degree tilt for the accreting material. And so the movies are going to play simultaneously in all three frames. And so so accretion starts. Initially, there is this strong differential precession, but it rapidly saturates and actually relaxes back. And so there is some differential twisting, but it's sort of fixed in time after sort of a very short initial period. And now what's happening, there's still a torque acting on this disk. It's just instead of the torque causing the disk to twist relative to itself, it causes the entire disk to precess globally, all right? So it's a little hard to see in this movie and this animation. So this was a simulation we ran later, where we ran this simulation long enough that you could actually see a full precession period. So this, probably convince you a bit more that the whole structure is globally precessing. Okay, so it started out tilted 15 degrees this way. Now we're sort of precessed 90 degrees and it's tilted kind of that way. Now we're at about 180 degrees of tilt, so it looks like it's tilted the other way, or 180 degrees of precession, sorry. And now it's at about 270, so you're looking down into the top a bit more. And then at this point, we're getting close to 360 degrees, so one full precession period, okay? All right, so lens during precession can have really interesting effects on an accretion flow, all right? So that's sort of the background, the things that I feel like you need to know in order to follow my argument. So everybody good so far? Okay. All right, so the paper, the argument I made is based really on just sort of three core premises, all right? So the first premise is that type C QPO that I mentioned is best explained by lens during precession. And this sort of kind of the most important part for me to try to convince you of. So I have a few arguments for why I think this premise is true. So one is it fits in with a relatively simple picture of how these outbursts proceed, called the truncated disk model. And the basic idea of the truncated disk model is when these systems are down basically in the quiescent state, what you have is a thin sort of Shakura-Synaev disk that's truncated at some large radius, inside of which you just have some hot, thick, fluffy, not radiatively efficient flow. And as the outburst proceeds, one of the things that is happening is the mass accretion rate is increasing. This can't be the only thing because there's hysteresis, so there has to be something else. But as the mass accretion rate goes up, the thin disk pushes in closer to the central object, which makes that hot, thick region become smaller. And as the hot, thick region becomes smaller, then that precession is going to be faster and faster. And so that actually fits in well with the fact that we see the type C QPO actually cover a range of frequencies as the outburst proceeds. So at the start of the outburst, when you first begin to see the type C QPO, it's usually at a pretty low frequency, around 0.1 hertz. And then as the outburst proceeds, the frequency of the QPO builds up and sort of hits its limit at 10 or so hertz, all right? So that's observations of the range of frequencies you see of the QPO transverse through during the outburst. And then if you sort of make a naive sort of, you take this sort of picture of truncated disk, hot, thick flow, and you let that hot, thick flow be the thing that precesses, then you can actually sort of work out what the precession frequency is. And it depends strongly on the size of that hot, thick flow. So as the hot, thick flow gets smaller and smaller and smaller, the precession frequency goes up. And the range of frequencies you get, at least with a very naive model, is about 0.1 hertz to 10 hertz. And it's not strongly dependent on spin, actually. So that's actually a range of spins from relatively low to relatively high spin. So it fits in well with this idea that as the outburst proceeds, this hot, thick region gets smaller and smaller, precesses faster and faster, the QPO frequency goes up. It also agrees with another observational discovery, which is that the QPOs are more prominent or are stronger in higher inclination sources than they are in low inclination sources. So if you just look at sort of fractional RMS, which is basically the power in the QPO, sort of how much is your signal varying, that fractional RMS is higher for sources that we know have relatively high inclination, meaning you're viewing them almost edge on, compared to ones that we know have low inclination that you're viewing mostly face on. And that makes sense in a precession model. Precession is much more noticeable if you're looking at the object from the edge than if you're looking at it face on, okay? Similarly, another thing is the QPO, the observers have measured what's called phase lag in the QPOs. So this is, you look at when the QPO arrives in the hard X-rays versus when the QPO arrives in the soft X-rays, and they notice that there's a lag between the two, but they notice that the lag depends on whether it's a high inclination source or a low inclination source. Low inclination sources show positive lag, high inclination sources show negative lag. And that can also be explained. There's multiple effects that would cause a phase lag. And we expect one of the effects, the solid angle effect, basically how big on the sky is the X-ray emitter, is going to be more sensitive at high inclination, or it's going to be more dominant at high inclination. Whereas Doppler effects, so the fact that some of the material is being beamed towards you and some of it's beamed away from you, is going to be more dominant in low inclination sources. And so that might explain why you get one type of lag in the one source and the other type of lag in the other source. Those two observational facts by themselves already argue strongly that whatever the QPO is, it has to be some sort of a geometric effect. It's something changing your viewing angle or the solid angle or how you're seeing this thing. Doesn't necessarily have to be precession, but it's something geometric. Another thing that this model sort of predicts, I mentioned the reflection feature. So whatever this corona thing is illuminating the disk and creating a reflection feature. If we take this hot, thick flow to be the corona, and so the corona is the thing that's precessing, then that means sometimes the corona is going to be illuminating the side of the disk that's coming towards you, and sometimes the corona is going to be illuminating the side of the disk that's going away from you. And so that means the reflection feature should sometimes be blue shifted and should sometimes be red shifted, and it should be in phase with the QPO. And at least in the one source where we've been able to pull this out of the data, okay, this source here, we actually do find that the iron line undergoes red shift and blue shifts. This is one of the reflection features. It's an iron line feature. And it is shifted in phase with the QPO. And so that very strongly supports that this type C QPO has to be caused by precession of whatever the source of the hard X-rays is, all right? Now, the last thing you could ask is, well, does it have to be lens-Turing precession? Maybe it could be some other kind of precession, all right? And so one of the things that people have always kind of been concerned about with lens-Turing precession is that it requires tilted orbits. And people say, look, are all accretion disks going to have tilted orbits? I don't know the answer to that, but I can at least argue that there is evidence in some sources where we have data to consider that at least some of these sources do have tilted or misaligned accretion flows. Now, I should say most of this is based on the assumption that the jet tells you what the spin axis of the black hole is, and that's the big unknown. Is there's no way to directly measure how the spin axis of the black hole is oriented. There are also theoretical arguments for why these X-ray binary disks maybe should be misaligned or tilted. So there's basically two primary formation avenues for X-ray binaries. One is coevolution of a pre-existing binary. One of the stars is more massive than the other, so it evolves faster. It undergoes a supernova, which creates the black hole that now becomes the X-ray binary. If that supernova is asymmetric, if it can provide a kick to the binary at the time of the supernova, you can reorient any pre-existing, spins and introduce a tilt or a misalignment at the time of the supernova. The other formation avenue, at least in dense stellar environments like globular clusters, is some of these X-ray binaries may form from binary capture or binary replacement. So the black hole is just passing through this dense stellar environment and either captures a companion star or replaces a lower mass star in a pre-existing binary. And in that case, the spin of the black hole knows nothing about the binary that it just joined, so it will almost always be tilted in that case, all right? So there's at least reason to believe that some, if not many of these systems could be tilted. And then my final argument on this is I can't think of any better alternative to what could cause precession for a black hole X-ray binary system other than lens-Turing precession. So if people have suggestions, I'd be happy to hear them. All right, so now we move on to premise 2. So premise 1, the type C QPO is best explained by lens-Turing precession. Premise 2 has to do with the fact that relatively recently we have started discovering optical UV and infrared QPOs at very close to or the same frequency as the X-ray, the type C X-ray QPO. So this is that GX339-4 system again that I've mentioned. Here's the X-rays with the QPO. That was one instrument. This is a different X-ray instrument, okay? But you can see that QPO in the X-rays. But this also now shows a QPO in the optical and a different optical band, and even in the infrared band. Now, in this particular case, they aren't all at exactly the same frequency. They're close, sort of within 10% of each other, roughly, but not exactly the same. I'll show you some others where they seem to be even more similar. And the point of this is, particularly the infrared QPO, almost certainly can't be coming from the disk. So infrared emission in an X-ray binary would be coming from very, very far out in the disk. And there's no way to think that that far out in the disk, things are varying on timescales of 1 hertz or something. So the primary thought is that these optical and infrared QPOs are evidence for precession in the jet itself, all right? So what you're seeing is emission coming from the jet, and the jet is precessing, presumably because the X-ray emitting region is also precessing, all right? So that's the basic idea. And this is now seen in multiple sources. So this is a different source. There's the QPO again in the X-rays. There's a QPO in the optical. And in this particular source, they were able to follow both the optical, the X-ray, and a UV QPO over many, many days. And they found that all of the QPOs varied in frequency together, all right? And so that certainly strongly argues that whatever is causing the optical QPO and the UV QPO and the X-ray QPO are all coupled together, okay? So then it's consistent. If the X-ray region is precessing, then it would also, you might imagine that the jet would be precessing, and that's the source of all of this QPO behavior. And here is yet another source. This is a popular source right now. These are 3 different X-ray observations on 3 different dates, showing the QPO at different times. And this is an optical observation in between these 2 X-ray observations, also showing that QPO. And this source was this is the first source where a QPO was discovered in very, very high energy emission, at least for an X-ray binary. So they discovered a QPO in the 200 keV and above X-rays. And they argued as well that that QPO was evidence of jet precession. All right, so, so this isn't direct evidence for jet precession, but it makes a nice consistent sort of model. And we know that at least some jets in nature do precess. One of the classic, probably the most classic example is SS433. This is an old VLA image where you can literally see the corkscrew shape of the jet plasma coming out from this system. This is a somewhat newer ALMA image of the same thing, where again, you can see this corkscrew of plasma coming out. I'm not arguing that this one is lens during precession, just showing you that we know for sure that jets can precess in nature. This is an X-ray binary system V404 SIG, where in radio observations, what they discovered was a very rapid, on the timescale of a few hours, change in the position angle of the radio emission on the sky. So basically, the radio emission went from pointing one direction to a few hours later, the radio emission was pointing in a different direction. And their argument was that the best explanation for this rapid change in the direction of the radio emission is that they're observing a precessing jet. And then for those of you who maybe care more about AGN instead of X-ray binaries, this has been seen in multiple AGN systems as well, where there's a change in the position angle. So the radio emission seems to be aligned that direction at that epoch, and in this direction at this epoch. The timescales here are obviously much longer because this is a much more massive system, but that model is basically a precessing jet model fit to their data. And so they argue that this fits very nicely for this AGN system. Okay, so jets precess, and maybe they precess in sync with the disk component. And so now finally, this is, Center for Computational Astrophysics, to start connecting to some of the simulations and things. So this is some simulations by Matthew Liska of tilted accretion disks, similar in vein to what I showed you from my earlier work, except in my earlier work, we really weren't able to follow the jet or say anything about the jet. But Matthew was able to break it down and follow the orientation of the jet, the disk, and something he called the corona. And the point is, this is two different simulations. The top panels are looking at tilt, and the bottom panels are looking at sort of precession angle. And the takeaway point, the thing I want you to take away from this is basically all three components precess together. And in this simulation, again, all three components precess together. So this picture of a disk, a hot, thick disk, or corona, whatever you want to call it, precessing with the jet seems to be consistent, at least with this class of simulations here, and seems to explain the observations quite nicely. Okay, so premise 3, where do we run into a problem? So premise 3 is that MADs, so these magnetically arrested disks, do not precess, all right? And there's now observational evidence, well, not observational, there's simulation evidence to suggest this or support this. So this is work by Sean Ressler, Chris White's a co-author on this work. So what we have here, again, we have accretion onto a rotating black hole. This movie is going to be oriented with the spin axis of the black hole up. What you're mostly seeing here is this greenish material is the jet. And initially, obviously, the jet is tilted with respect to the black hole. But as this simulation proceeds, so on a time scale, very, very, very short compared to like the outbursts cycle that we've been talking about, the jet realigns itself with the spin axis of the black hole. And this happens, so Sean basically did some, his simulations go between MAD states and non-MAD states. He doesn't see this alignment when it's not MAD. He only sees this alignment when the simulations go MAD. And so Another way to kind of see that is if there's no spin of the black hole, then the jet doesn't reorient itself. It's reorienting itself as a consequence of the spin of the black hole. And this is the disk realigning itself. And this is the jet. And the jet realigns itself basically on the same time scale that the disk does. Okay. So when this system goes into the mad state, the disk and the jet realign. And then the point is, if it's aligned, if there's no tilt, then there's no lens during precession. There's nothing to cause precession in this case. All right. And then these are simulations by Kaushik Chatterjee. These are somewhat, in one way, more controlled simulations where he just starts with a torus that he forces into the mad state, and he starts with some tilt, 15, 30, 45, 60 degrees. And what he finds in basically all of these cases is that the inner disk aligns with the symmetry plane of the black hole. It does so relatively quickly, and it stays aligned for the rest of the simulation. So this is a space-time diagram. The color represents tilt. So the inner part of the disk aligns quickly, and then the rest of the disk begins to align with it. And then this is looking at the tilt of the jet. It's the same story. Once the disk aligns, the jet ends up being aligned as well. And so it seems that the MAD simulations promote alignment. And if you have alignment, then you can't have precession. All right. So that's basically the gist. So to explain why I focus on the luminous hard state, that just comes from the fact that the type C QPO is most prominent in the luminous hard state. So the blue stars here is when the type C QPO is seen. So that QPO is most prominent in this luminous hard state. Then if the type C and the jet QPOs are explained by lens during precession, and if MADs force alignment and prohibit lens during precession, that's how you reach the conclusion, or I reach the conclusion, that the luminous hard state then can't be MAD. All right. So what about problems or alternatives? You know, just to sort of anticipate if there's any pushback. So, you know, first off, you know, why has everybody been so crazy about MADs, mad world, MADs solve every single problem? MADs do seem to have their place in nature. A lot of time and effort has been spent in the last few years studying the results of the Event Horizon Telescope for M87 and Sagittarius A star. And the conclusion of most of that work seems to be that those two systems, the observations are best explained by MAD accretion flows onto the central object. All right, so here's a case for M87 where they're trying to fit these observations, and then sort of this band is the MAD model and that band is the non-MAD, and clearly the MAD fits better. And there are similarly papers that argue that Sagittarius A star is best explained by a MAD. So it seems that MADs do exist in nature in various places. So the question is, do they exist in the luminous hard state? And one of the things, putting this back in terms of the Q diagram, an interesting potential problem that this creates, if Sagittarius A star and M87 are they're both very low luminosity sources. And so they would be the equivalent to what I call the quiescent state here for X-ray binaries. So if they're representative of the quiescent state, and so if they're telling us that all quiescent black holes are MAD, and we're pretty sure, although there may be some debate about this, we don't think the soft state is MAD. So even if you don't believe my argument that the hard intermediate state can't, or the luminous hard state can't be MAD, we don't think this state is MAD. So it does seem, if they're mad in this state, they have to become unmad, I don't know, sane or happy or something at some point. So the question then is, what's the physics and how does the system know at some point I need to not be mad anymore? All right, so I think that's a really interesting open question. Another, just in terms of trying to think of alternatives, I mean, it's not like lens during precession is the only proposed model for the type C QPO. There's something called the accretion ejection instability that they claim that there's some orbital frequency associated with this feature that might be able to explain the type C QPO. It's not clear that this explanation is a good explanation for type C QPO because it doesn't seem to explain some of the geometric effects that I talked about. There's another model out there called JEDSAD. So just keep putting more acronyms into accretion physics. To me, this one doesn't seem a lot different from what I was proposing. I mean, basically, it's a truncated, Shikura-Shinaev disk with a hot, thick flow interior to that. And, they call it a JED because they say the jet is associated with that hot, thick flow, which would explain why the jet precesses with the hot, thick flow. So I'm not sure this is a lot different. They explain the type C QPO, though, as just it's an orbital frequency associated with kind of these transitions that they have. Again, it doesn't seem to match the geometric nature of the QPO. So I'm not sure. I need to work with this group more and sort of figure out if we can come together on some sort of agreement. But so there are alternatives out there, but I'm not sure that there are better alternatives out there. Okay, so what about the future? What can we do to try to resolve this discrepancy? So on the observational side, there's a couple ways to do this, and I had some interesting conversations today. One of them is to try to use X-ray polarimetry. So IXPE, the imaging X-ray polarization experiment, is about a year that they've been taking data so far. Polarization is sensitive to things like how's the magnetic field oriented, or if you're reflecting, it can be affected by sort of what's the orientation of the thing that's reflecting the X-rays at you. So the point is, IXPE should be able to tell us something about the structure of the flow. And in particular, if the structure of the flow is changing in some periodic way, then probably the polarization angle should be changing in the same periodic way. So that's one way you can go about it. Another is to just study the QPOs more carefully and more systematically. Most of the really good work on QPOs was done back when we had an instrument called the Rossi X-ray Timing Explorer. That's sitting at the bottom of the Pacific Ocean now. And we haven't had a good X-ray timing mission in a while. And so there is a proposal, one of the mid-X calls from NASA for something called StrobeX, which would be a high time resolution, wide field monitor to look for timing features, for instance. Maybe more interesting to this crowd is what could be done on the simulation side. And I just think we need more simulations of tilted accretion disks. We need, we're starting to get a wider range of tilts. Part of this is me. I've just always done 15-degree tilts, but people are starting to do a wider range of tilts, a wider range of spins. We need to start varying the starting conditions instead of all of us starting from a torus, a donut. And we need to start looking systematically at differences between mad and non-mad simulations. The idea being is, maybe the handful of simulations that I've looked at so far of tilted mad simulations that all seem to show alignment, maybe that's not the whole story, okay? So that's the idea. All right, so that's basically the end of my talk. I always like to, at some point in my talk, show pictures of some of the students we take So I do most of my research with undergraduate students. We're an undergraduate-only department at the College of Charleston. I occasionally have graduate students and postdocs visit, so if people are interested in coming to Charleston. But most of the work's done with undergraduates. A lot of that happens in the summer. So we take group pictures every summer. So this is the last 8 summers at the College of Charleston with my research group. So I just wanted to acknowledge them. So thank you very much for your time. I appreciate it. And hopefully you have some questions.
Questions?
So I was wondering, when you mentioned that map does not persist, you showed the simulation and said that it's when you have strong spin for the black hole, map no longer persists, but is that mostly due to map being map, or is mostly due to the black hole having strong spin?
That's a very good question. And I think that's along the lines of we haven't done enough simulations to necessarily know the answer to that question. And I was having conversations, we don't really even understand exactly the physics of why those simulations that have aligned. Like, you can think of it as, okay, you've got a rotating black hole, the field attaches itself to the black hole, it sort of feels that rotation, so the field starts aligning, and because it's mad, it's a strong field, so it dominates the disk and it forces the disk to align. But you know, that's a sort of very simplistic picture of what's happening, and we're not sure that that's even the right picture. So yeah, it may be at lower spins, maybe a mad still does persist. The thing to keep in mind there is you have competing effects, right? At lower spins, the lens-Turing precession is weaker, but also maybe the mad alignment is weaker. And that's getting into the environment of why do we do numerical simulations? Because you have these competing effects and you don't know which one's going to dominate, and you just kind of have to stick it in the computer and see what comes out. So, yeah.
So you had mentioned that some of the hard but lower luminosity systems might be in a quiescent state, and then the harder, more luminous might be the lens-Turing. Do you have any conjectures or ideas currently about what might cause a transition between those states?
Let's make sure I understand what you were saying. So, as far as, so I mean, I think it may be this, let's see. So we're talking on the hard side of the spectrum, right? The difference between quiescence and luminous hard state. So I think physically, all that's happened, I think that side of the diagram is well explained by this idea of the truncation radius moving in closer and closer and closer. So the accretion rate is getting higher and higher. So the luminosity of that hot flow gets higher and higher. It becomes more and more luminous. If your question is like, why do we not see the type C QPOs down in quiescence? My argument there is just that hot thick flow is so big that the precession timescale is just so long that they just never found it yet, because they don't look for QPOs in the, you know, really, really low. They also is the signal is probably a lot weaker at that point, because you're competing now with just, you know, turbulence and things, and it's not going to dominate as much. So, but that's one of the things that maybe Strobex would help, is if you could probe for these QPOs at lower and lower luminosities and really trace how the QPO frequency changes with time. They usually only, like I showed on that diagram, they only usually catch that type C QPO as you get up to the very luminous, but it may have been there earlier and they just couldn't see it. And so a new instrument that might be able to trace even more of that evolution might teach us some things too. Yeah.
Great, thank you.
Yeah.
There's a question on Zoom from Brian.
Hi, Chris. Good to see you. Enjoyed your talk. I was curious if you think there's any role. I mean, I know some other people have found that the inner disk can break if you have sufficient misalignment. You can actually break the disk into rings that precess independently. Do you see this in any of your simulations, and do you think it contributes to any of the phenomenology of these binaries?
Yeah, no, that's a good question. Thanks for the question, Brian. So I have not seen the this disk breaking effect in my simulations, but I have never pushed my simulations past about 30 degrees of tilt. And this breaking usually only happens at fairly extreme tilt. And so for me, at least, that makes me worry about that phenomenology being able to explain. For instance, the type C QPO is seen in basically all sources in their outbursts. And there's even an analogous type C QPO in neutron star systems. And so it's hard for me to believe that all sources that show a type C QPO have 60 degrees tilt or more. And so while I think the tearing phenomenology is really interesting and probably plays a role, certainly in like probably tidal disruption event type disks and things. I don't know in X-ray binaries. I certainly wouldn't expect a high percentage of X-ray binaries to have tilts of 60 plus degrees.
Okay, thank you.